Hello everyone, good morning. And I am Ansh Bhardwaj from Engineering Physics third year. And my title of project is Radiomics based classification of brain CT and MRI scans. So, my work began on very practical observation that in medical research repositories and hospital archives, we often encounter thousands of brain images where metadata are missing, mislabeled, and inconsistent. Knowing whether a file is CT or MRI is fundamental before any further analysis. Rather than manually verifying or relying on DICOM tags, which is digital image and communication in medicine tags, I wanted to build an automated system that can distinguish CT from MRI scans directly by looking at image characteristics themselves without any manual annotation. To achieve that, I implemented a full pipeline starting from raw DICOM data, converting it into Neuroimaging Informatics Technology Initiative, which is an open source file format for storing CT scans, extracting radiomic features into it, then describing the image texture, image intensity, and statistics, and finally training an XGBoost classifier to tell whether it is a CT scan or MRI. The beauty of this approach lies in its simplicity, interpretability, and we are not using any deep black boxes, rather than we are using simple machine learning models. So the project goal is to automate the distinction between two primary medical imaging modalities, that is MRI and CT scan, based purely on extracted radiomic features, and it is to demonstrate a robust end-to-end medical imaging machine learning pipeline from raw DICOM data acquisition and pre-processing to trained model deployment. Moving on the pipeline that I planned. So the pipeline which I initially planned was to use two kind of data sources into it. The first was IXI dataset, which is this one, which had several types of images. The first was T1, which are T1 weighted MRIs. These are highlights of fatty tissues and shows anatomical details. The second was T2, which highlighted water and fluid. PD was used for hydrogen atom density. MRA shows blood vessels, and DTI measures water diffusion. This is what I used for MRI. Then I used CQO 500 dataset to get MRIs, CTs that had 451 computer tomography scans with 193,000 slices. After that, I pre-processed them and converted those DCOM images into NIFTI, normalizing voxel spaces. Then I proceeded with feature extraction, generating quantitative radiomic features using PyRadiomics, and finally modern training, where I trained it using XGBoost for binary distinction. After that, I evaluated it on accuracy, AUC, and feature separation. Moving ahead, I used two kind of datasets. The first was IXI dataset, as I explained. It captured soft tissue contrast based on hydrogen nucleus relaxation time, the ideals for distinguishing in any gray matter, white matter, or cerebral spinal fluid. To make this more good, IXI dataset had more than 500 MRI scans collected from various London-based hospitals. For this, I took out around 50 of them. Let me show you image of one of them. So this this is one of the scans which I got from it. So these are the type of scans which are present in IXI dataset. Then I proceeded with CQO dataset, which included CT scans provided by Query for academic research. Again, I selected 100 of them. For each MRI or CT volume, around 150 Excel slices of around 256 by 256. To make sure processing manageable, I used a balanced sample of 80 each, while ensuring that both datasets cover normal brain anatomy. So this is the code that I used. This was wget http. This is where the IXI data was present and the CQO data was present in a torrent file. Then moving ahead, these are the types of images that were present. The MRI texture IXI exhibits subtle, finely detailed variations in intensity measuring. So CT, which is computed tomography, measures the X-ray annotation coefficient of tissues, which is directly related to density. It is great for bones and acute hemorrhage. While MRI, which is magnetic resonance imaging, measures hydrogen proton relaxation times, giving us exquisite soft tissue contrast, gray matter, white matter, and CFS shows distinct intensities due to T1 and T2 differences. So, T1, T2 differences, which I told before, that are highlights fatty tissues and water and fluid. So, from a signal processing perspective, CT images are characterized by high contrast but low texture complexities, while MRIs have high texture variability. So, these were the two databases which I used. So, this is one of the MRI bit slice which I got, and CT scan. from the CQO database. Moving ahead in the standardization and preprocessing. So standardization preprocessing was a crucial step in it. After conversion, I verified both the datasets originally come in DICOM formats, thousands of 2D slices per study. To handle them uniformly, I used DCM to NIAXX, which is an open source converter, to transform DICOM files into NIFT files. Conversion was very important because NIFT is an open source material in which both of them can be easily processed and features can be extracted. The conversion also compresses the data, preserves spatial metadata, and allows for easy loading with NiBible and simple ITK. Next, I sampled all the volumes into an isotropic voxel sine of 1 millimeter cube using cubic interpolation. Without this resampling, texture features could vary simply because CT and MRI scanners have different pixel spacing. But I uniformed that. So DICOM and NIFT conversion was taken place like this. DICOM folders were taken in place. DCIM was used, voxel was the taken, and NIFT was finally extracted to get the brain outline. This was the code which I used. So the initial process was to convert DICOM into NIFTI, for which I used DCM to ANX. Then all the scans were resampled to consistent isotropic voxel spacing of 1 millimeter cube to prevent feature measurement from being skewed by resolution difference. And binary masking were generated using Otsu thresholding, restricting feature extraction solely to brain parenchyma. Okay, so we start by defining a function called expand 500. Its job is to automatically unzip CQO 500 dataset, locate the DICOM files in it, and convert them into NIFTM4. So by doing so, next I use globe module to find all the NII NXI 500 files and the zip files which are already converted, and to convert them into DICOM files. I have turned on the recursive because I want all the inner files to be extracted out of it. Then post that, for every zip file found, I created a separate folder inside CQO 500 unzipped with using the zips name by mkdiring and making sure that parent's name was present. Now the most important steps comes in when I use the subprocess module to run the unzip command through the terminal, and the -n flag prevents overwriting of existing files, and the input is redirected to pipes to clean the console clean. After extraction, I search for all the DCM files, that is DICOM medical imaging format as I said before, and store the parent folder that contains them. This gives me a list of directories where DICOM scans are located. After that, I initialize an empty list that is converted. If DICOM directories exist, I make sure there is an output folder called CQO 500 NIFTI where all of them are stored. Now I loop through all the DICOM directories using TQDM to show a progress bar as I wanted to see the progress of it. Each folder is assigned a unique name generated by hashing the folder path to avoid duplicate names. Here I called DCM to NIXX tool. This is standard command utility line to convert the DICOM into NIFTI files. The -ZY flag converts the output O from the output directory, and -F defines the file name. Once the conversion is done, I use globe again to collect the NII files that were created, and finally the function returns all the combined unique list of NIFT files, including both the previous existing and the new ones. In short, the function automates the entire CQ500 data preparation process, from unzipping to scanning DICOMs to converting them into NIFTI format and collecting their final path. Moving ahead, so is the code that I primarily used. So next comes that radiomics feature extraction. With the standardized images that now we have of both of them, we can move into heart of this project, that is feature extraction, for which I used PyRadiomics library, which implemented the IBSI standard definition of radiomic features. For each volume, PyRadiomics computed several categories: first order statistics such as mean, variance, energy, and entropy; texture features like GLCM, GLRLM, GLSZM, and GLDM matrices capturing spatial intensity relations; shape features, which are describing the 3D geometry of the area. Each scan ultimately yields over 100 features, effectively transforming every image into a numeric vector. These form our input table for machine learning, the code of which is here, that I imported feature extractor from radiomics, and I applied them with the width of 25 and turning on the normalization across all of them. Once that is out of the way, here comes the feature distribution. The after everything that we saw, the first order energy was in 21,000 images and 75,000 MRI values. Since MRI scans were less, that is why there is a significant difference. Texture contraction in 8,000 images, and here 3,000 images. First entropy in 6,200 images, and mean entropy in 5,800. Similarly, shape was varying in 1.25 and 1.3. Features derived from intensity, example of like energy and spatial relationship like contrast, show most distinct ranges which strongly differentiate the modularities. Now we use feature separation via MCA. I think this image has glitched out, but okay. After I reduce the multiple features into two dimensions using PCA, that is principal component analysis, like I did in the previous slide, where I took out features like first order energy, texture contrast, feature first order entropy, and shape volume. After doing the PCA, each point on the scatter plot represents one entire brain volume in radiomic space. Each, even without any labels, two clear clusters emerge, one for CT scan, that is this one, and one for MRI. This visualization proves that extracted features incoherently encode modality. Okay, so I fixed it. Moving ahead, so this is the plot which I was talking about, that PCA projection of radiomic features. We can clearly see that CT scans are present here in the cluster, and our MRI scans are present here in a cluster. Then this visualization proved that extracted features inherently encode modality information. It also serves as a quick sanity check for data quality before any training classifier. After that, so the 2D projection of the feature matrix onto the first two principal component analysis, PC1 and PC2, shows clear non-overlapping clusters of MRI and CT scan. This separation suggests that variance captured by leading principal components is primarily driven by modality-specific textural and intensity differences. Now comes the special part. For modeling, I selected XGBoost, short for Extreme Gradient Boosting. Why not neural networks? Because our data set is small and the feature count is moderate. XGBoost builds hundreds of shallow decision trees sequentially, each correcting the error of previous one. It handles non-linear relationships, works well with tabular data, provides built-in feature importance metrics. Moreover, it trains in seconds on computer and gives excellence generation. So while CNNs are powerful for raw imaging tasks, XGB remains unbeatable for structured radiomics data. Okay, so let me get to the code now. This section builds on the radiomics machine learning model using XGBoost, which is powerful gradient boosting decision tree algorithm ideal for tabular structures like radiomic features which we have. So initially I import the XGBoost and give it a short alias for XDB for easier use. Now comes the most important part of the parameters. So the objective of it is binary classification, so I set it to binary logistic. It tells the model we are solving a binary classification problem. Output values are between 0 and 1. For the max depth, I set it to 3, that is the tree depth. It controls how deep each tree can grow. Smaller values help prevent overfitting. ETA is the learning rate. It controls how much each new tree contributes to correcting the previous one's error. Subsample, that is 0.9, means row sampling uses 90% of the data for each boosting round to make the model more robust. Call sample by tree, which is feature sampling, uses 90% of the features for each tree to avoid overfitting by not taking the 10%. And eval metric was AUC, that is the evaluation metric that we use was area under the curve to evaluate motor performance during the training. So the input was radiomic features, around 80 feature scans per scan, and output was probability of CT versus MRI. The data was split into 30 scan training and 10 validation sets. Early stopping mechanism were implemented, tracking AUC and extraction to prevent overfitting. This was the graphs that we obtained. So monitoring key metrics during the boosting process confirmed rapid convergence and model stability after a low number of iterations, demonstrating the predictive power of radiomic features. So this was the training curve, accuracy versus number of iterations. This is AUC and this is our log loss. So after 120 rounds, stability was achieved. The model achieved the maximum performance and stabilized its metric tracks around 120 rounds. Peak validation score was 97%, achieved a high classification accuracy on the held out validation set, confirming the strong generalization ability and a 0.99 area under the curve was achieved. The receiver operating characteristics AUC approached the optimal value, indicating an excellent separation between the two classes. As we saw that the clustering was clearly visible in past, so that is why it was easy to train here. Now that the validation metrics and initial model results are here, our initial validation focused on three core metrics: AUC, overall accuracy, and log loss. These parameters provide a robust way of measuring the model's performance, especially in binary classification tasks. With the AUC score of 96, a classification score of 97.4, and after 120 total rounds, we got our final model. Now that we have everything here, our let's get to the feature importance interpretation. Feature importance analysis helps us interpret the model. XDE boost computes how each feature compute to reducing the error. The top features were entropy, contrast, energy, and correlation. All texture descriptors. This aligns beautifully with imaging physics. MRI soft complex tissues generate higher entropy and contrast, while CTs, uniform densities, yield higher energy and lower correlation densities. Entropy measures the randomness and complexity of the image texture. Contrast measures the local variation in the gray levels, the sharpness. Energy measures the uniformity and consistency of image texture, while correlations measure the linear dependence of gray levels of nearby voxels. Moving on to the model interpretation part. Now we come to the feature importance directly correlate with the fundamental physical principle and information of quality. MRI textures had lower uniformity and higher entropy, while CT textures had lower entropy and higher uniformity. These were the major two features that our model took into account while dividing where should each scan go. MRI's main characteristic included they exhibited higher intensity variability, diverging driven by diverse T1 T2 weighings. This led to greater texture complexity and higher entropy values. The rich soft tissue contrast contributes significantly to radiomic separability. CT scan characteristics typically show more uniform in soft tissue voxels, results in lower entropy and higher energy values. Intensity values were primarily reflect from electron density and attenuation. Now for our pipeline, this figure summarizes the entire system. We have, I think, so here data ingestion. We securely loaded anonymized imaging data. We pre-processed it by converting into standardized format by converting DICOM into an FTI. Automated calculations of hundred of texture features. We created a feature matrix, created a structured input ready for machine learning, XDE boost classifier, training and hypermeter tuning, performance assessment using IUC, accuracy and log loss. So we ingested the data, pre-processed it, standardized it, used radiomics and extracted a feature matrix. Now once this was done, let's get to actual applications of it. Beyond simple classification, this methodology offer several tangible applications from improving efficiency and analysis in clinical radiology settings. So one of them was ensuring data integrity and correct labeling with image archive. Second was modality verification, automated checking of large diverse datasets for consistency, diseases phenotyping, extending feature-based analysis to identify subtle disease subtypes, and real-time flagging. Integration with hospital PCAS systems for immediate alerts on mislabeled stuff. Clinically, this kind of system has multiple applications as told, like in hospital archives it can automatically verify modality tags, prevent mix-ups in large image repositories. For research consortia it can pre-screen heterogeneous datasets before analysis. More advanced versions could even flag inconsistent series with a multi-model study or perform automated quality control. The same methodology can be further extended to example differentiating between MRI sequence T1 T2 or detecting scanner related artifacts. Now the limitations of this are extremely big. Despite the strong results, several constraints limited the scope of this initial study, pointing towards the crucial areas of future development. Limited generalization with a data set of around 20 subjects per modality restricted the confidence in performance across heterogeneous patient population and different scanner types. Next of the limitation is basic masking strategy. A simple non-segmented brain mask was used, potentially including irrelevant background noises. in feature extraction processes. No deep learning comparison. This analysis relied solely on classical texture radiomics, omitting a critical comparison with performance achieved by deep learning convolutional neural networks. Finally, this is the strategic map for future work, which includes the next phase of research will focus on scaling the study, incorporating advanced techniques, and developing a deployable clinical tool. The To start, we'll be expanding our datasets, targeting a sample size of exceeding 500 images to a high external validity and robustness, comparing radiomics with CNN, directly comparing the predictive power of traditional radiomics features against deep embedding from pre-trained CNNs, implementing a 3D segmentation by utilizing precise 3D segmentation of specific anatomical structures and multi-parametric inputs volume for enhanced feature fidelity. And finally, developing a web app deployable that can translate our model into user-friendly web-based suitable application for clinical screening and overall use. Conclusion: from pixels to patterns, AI in medical imaging, we did radiomics efficacy confirmed. Radiomics features derive simple mass that can be reliably and accurately differentiate CT and MRI. Classical ML values were used. Highly powerful, highly performance XG boost model demonstrates that classical machine learning techniques remain highly relevant in complementing complex deep learning approaches. And this was foundation for automation. This work establishes a robust, explainable foundation for automated modality detection and uh, quality assurance in the vast medical archives. This was my presentation and my work. This was the dataset which I used. These were the files which I had, and this was my final code. So, thank you so much. Have a good day.